conosciuti in Canada, in British Columbia, tantissimi anni fa, non un simposio. Io non leggo tutte le, troppe le cose su di lui che si possono leggere. So dire che è il capo del centro Orno Linear Studies, che è un centro di eccellenza estone di ricerca, con molti contatti, specie con i paesi nordici, perché sapete che l'Estonia è in su, davanti alla Finlandia, e ha contatti con la Svezia, con i centri di ricerca del nord. La sua ricerca principale ha svariato in campi diversi, anche se vicini, dalla meccanica teorica alla fisica matematica e alla biomeccanica, e attualmente si occupa soprattutto di dinamica non lineare e di complessità nel senso nostro, se no la professoressa non quella informatica, complessità come la intendiamo, come intendono i meccanici, e come le meccaniche dei continui, di elasticità non lineare, propagazione di onde. Ha vinto tanti premi, tra cui voglio ricordare uno molto importante, che è il premio von Humboldt, quindi è stato un vincitore von Humboldt. È membro di una certa lista di accademie che non elenco, è stato per tanti anni presidente dell'Accademia delle Scienze estone, è stato presidente dell'ALEA, cioè All European Academies, l'associazione delle accademie nazionali europee, e grazie ai suoi buoni uffici questa accademia da poco tempo è entrata a far parte dell'ALEA, anche perché parlandone ricordate che quando questa accademia è nata come Accademia del Regno di Sardegna, quindi nazionale, e poi le vicissitudini della storia ci hanno portati che l'unica accademia nazionale italiana è quella di Vicenza, con un accordo con Vicenza che non c'è entrato, e grazie ai buoni uffici di Juri. È stato un carico importante ricoperto nell'Euromed Council e nello Utah, che è l'Unione Internazionale di Meccanica Teorica Applicata, è molto grande e importante, e sempre però collegando i suoi interessi alla complessità e a numerose pubblicazioni. Lui si è anche occupato molto di politica della scienza, politica anche per i finanziamenti, perché sine pecunia non la scienza, ci sa, è difficile, e non vi dico, è stato decorato da vari ordini estoni, finlandesi, francesi, polacchi, belgi, finnici, da tanti che non sto a ricordare. L'ultima sua opera che è uscita quando? Questions about elastic waves, un argomento di cui siamo occupati, lui molto più di me, comunque siamo occupati da molti anni sulle onde in elasticità non lineare, ma anche in solidi con struttura complessa, voglio dire con differenti scale, cioè un corpo elastico non lineare con microstruttura è una struttura complessa in quel senso. E poi si è occupato molto, e ora si parlerà di quello, dal titolo dei modelli matematici di sistemi biologici, che è un problema, è ovvio che è molto complicato, perché bisogna tener conto di fenomeni non semplici come l'eccitabilità o gli scambi di energia, i vincoli termodinamici, le gerarchie di interazione tra i livelli diversi delle componenti con scale diverse. In questo intervento l'attenzione di Juri si concentra sulla propagazione degli impulsi nervosi e gli effetti collaterali, diciamo. I modelli matematici sono basati ovviamente su considerazioni fisiche, con delle ipotesi che consentono di tener conto degli effetti principali, i leading effects, che non possiamo tener conto di tutto, se no non si riesce a costruire un modello trattabile. Ottiene delle equazioni di campo e escono da queste equazioni, come dire, delle equazioni di tipo di evoluzione o di tipo di Bussineschi, e dando origine si trovano degli impulsi asimmetrici solitari con delle componenti sottostanti che possono portare a regimi caotici. L'onda meccanica nella biomembrana può essere un'onda solitaria dovuta questo è tipico quando in queste strutture, in questi modelli si trovano delle studiano delle onde, che l'onda solitaria, il solitone, lo tsunami che piace per parola ai giornalisti, ma intanto per l'onda solitaria, trae origine dal fatto che c'è un bilanciamento in qualche maniera tra la non linearità, la dispersione e la dissipazione. E il problema è quello di determinare i parametri dei modelli matematici dai dati sperimentali, e questo è un problema cruciale, sicuramente non è facile. Cedo volentieri la parola e lo ringrazio per essere venuto qua a trovarci e a raccontarci queste cose. Grazie.
Mr. Chairman, ladies and gentlemen, thank you very much about this introduction. I'm sorry that I have to speak in English, that my Italian is very poor. I can manage, but not to give a lecture. Maybe next time. Actually, it's not the first time I'm in this hall, but this is a very special time indeed for me, because the first time I'm here as a foreign member of the Academy of Sciences of Turin. And this is a big honor, and I really appreciate this very much. We agreed that I shall speak about biological systems and mathematics. And Franco, did I understand correctly? It's about 40 minutes or
40, 50,
something like that.
Not a strict time.
Yeah, thank you. So, my home institute, or my home laboratory, is the Center for Nonlinear Studies. It means that we really deal with nonlinear processes in many aspects. Waves in solids, waves in fluids, biological systems, and optics. So that it covers really quite many interesting physical processes, and we try to put them together and to use this sort of, joint efforts of people whose background is mathematics, is physics, is biology, so that really to put it together and to get the synergy out of it. What I'm going now to speak about is a little bit about the biological system, and actually what is the main problem later on. It's a nerve pulse propagation. This is a very interesting topic, a very interesting history, many very special results, and seems that it's something that we have to understand, and we have to really to model and to understand by modeling also this physiology behind it. Because in this case, it's mathematics only cannot solve the problem. We have to be very closely related to the physiology. I would like to start with some kind of explanation about the biological systems, how we feel these should be modeled mathematically, or how they should be understood also on the wider level. And then I come to the nerve pulse propagation. First, this traditional part. But again, we have tried a little bit to modify these equations to understand a little bit better what is actually happening. But this is really the very wide range of problems. So I can only touch just the propagation along the nerve fiber, but not the networks, not the very special problems which are related to the consciousness and so on. And then, although it is well accepted that it's an action potential, that it's a main sort of, signal propagating, there are also the accompanying effects measured and understood a little bit, but not fully. And this is enormously interesting topic. I tried to come to some kind of mathematical models, and then I said to see that there is a one part of it. I said, don't see it, which is a little bit even heretical. As you see here, they're called mechanical waves. So first it seems that what is it? But I'm going to explain it. It's, the experiments are known, and this is exactly that's something that we would like to understand. And then later, as usual, some kind of discussion. Now, biological systems. Biological systems, if we speak about humans, about our organism, about the processes, there is something that should be stressed in the very beginning. The first, it's not exactly that sometimes it is said that the muscle is like a rubber band and we can really just have this contraction modeled by very simple models. No, there are hierarchies, there are various scales, starting from the general organism and organs and then just down to cells. And again, what happens in cells, where this is the most important element of these hierarchies, where these are the energy, actually, factors. Then, speaking about modeling, it's not only physics, it's very much chemistry. So the chemical processes accompanying this, whatever we speak about the physiology, this is something that must be taken into account. Ion currents, the concentrations, diffusion, and so on. And then, again, when you think a little bit about mechanics and the conservative systems, that's not the case for biological systems, because there could be excitability. You excite something, the activity, so that the active links between the components, certainly dissipation. And if we try to describe it by mathematics, then mathematics is pretty complicated. Again, the problem is that maybe we are able to just find the main elements and try to understand this mathematics, coming back to the experiment and so on. Nonlinearities, that's exactly what Mr. Chairman pointed out, that it's been the interest, our joint interest for many, many years already. Again, this is something that this must be taken into account. So, I'm not going to speak about hierarchies today, but about interactions, about excitability, and about complicated mathematics. So that is something that will be actually the outline of this talk. Now, nervous systems is certainly also quite complicated, hierarchical sense that there are nerve cells and axons and synapses and all what happens in our brain here. This is really such a huge system, and these networks, this is something that we have to understand. The present European project, which is called the BRAIN project, the European Union gave 1 billion euros for that. So that people from Zurich and from London are chairing these studies. But let us think about a little bit about the very, very such kind of simple thing. So this is a structure, very typical structure, where we have these actually the nerve fiber is here. Usually there is some kind of additional layers, like Merlin sees here, and some kind of special, well, the nodes here, this activity could be introduced. The nerve cells here is the different, and we are interested actually how signals propagates along this axis. The simple cases, for example, where this mathematical modeling started about the 50s last century, Hodgkin Huxley, they were interested in squid axon, and this was very simple, without any such kind of additional layers or whatever. It was just really the fiber, and then they could measure the signals. The signal itself is very important in many cases. We have been interested also, for example, in contraction of the heart muscles, and this is something that is really, it's well, something that everybody is interested in it. And the point is that actually it all starts from this very small place, like about this 5 by 5 by 5 millimeters, so-called sine node. This is the conglomeration of cells that produces the signal, roughly say, every second. And this signal propagates to the bottom of the heart and is distributed by these fibers called Purkinje fibers. Actually, as usual, nature is very careful. There is also another node, AB node. I lost this sort of. This is here as a sort of, a little bit like a delay, a little bit when the first node doesn't function, then the second node takes, but this is pathological already. And then the signal starts, actually. Here, this is the signal that is generated by the sinus node. And here is a signal that comes to this part of heart, and this is the signal for contraction. The good thing is that we can measure it, not exactly these signals coming down. The time goes here, as you see that it takes some time to reach the bottom of the heart. But what we actually measure is electrocardiogram. Electrocardiogram, and this is something that gives us a lot of information, information about the system, about how the pulses, how your heart functions, and so on. Now, what is important? Electrical signal called action potential and ion currents. Ion currents that really are related, that keep the signal going on. And in addition, again, there is a question sign now, mechanical waves. I'm going to explain them in some 15 minutes. So first, let us start with this action potential. And heat, also measured. Mechanical waves measured, heat measured. Certainly, it doesn't mean that you are thinking and then, oh my God, my brain is somehow hot or whatever. But the heat really can be measured, and although it's really, you need the very special devices, but nevertheless, this is something like that. Now, the structure. If we think about again, our some of our ideas come from solids with microstructures. This is a very special microstructure. The first, we have this is the nerve fiber, and this is now the so-called biomembrane. So you can actually take the nerve fiber as a, well, I'm sorry to say, but as a tube. And the two walls are very special, made of a very special type of molecules, and these are called lipids. Lipids bilayer, and it's hydrophobic, and these tails are inside. And the main point is that there could be some kind of gates so that the ions could penetrate the wall. And now, if we now come to the special case how the signal is propagating, then we can see that actually that inside it is usually the potential measured in millivolts is negative. The signal is then a very special asymmetric pulse, a solitary pulse, like here, and after it doesn't go to the immediately back to the equilibrium. There is an overshoot. And the main point here is that these sort of ion currents through the wall, these are the main mechanism that keeps nerve pulse propagating. Otherwise, it would be dissipated very quickly. Now, the structure, if we take the cross-section, it's again seems very clearly seen like a tube, and again inside it's the negative potential, and outside it's a positive potential. So the pulse propagates in this within the fiber, and what happens with the wall? This will be exactly now the next question. Well, not the next immediately, but after a certain discussion. The actual potential models, Hodgkin-Huxley model is very well known. That I'm going to speak a little bit about that. Pitts-Unal-Moore model is simplified. There is only one ion current. In Hodgkin-Huxley there are 3 ion currents. And I tried to also to derive such kind of evolution equation type, which is typical for fluid mechanics or solid mechanics. And then now, when we come to the section of potential, then it's quite clear that it starts from the telegraph equations. So that there is the voltage, there is a current I, V voltage, and there is certainly a resistance, inductivity, capacity, and so on. And there is ion current I here. What was done by Hodgkin-Huxley? It was in the 50s last century. They dropped inductivity and they reached the diffusion time bomb. It seems to be that it's a very simple, because this is really the diffusion here, these 2 terms. Everybody who is familiar with mathematical physics, this is one of the basic equations of the hyperbolic, parabolic, and elliptic equations, and this is parabolic equation. But the point is that there is this I here, and that makes it this interesting. And this brings nonlinearity into it. So this is the important point. And actually it's related to the ion currents, and related to the several these potassium and sodium conductances and the equilibria of those ions. So that this is actually, if we can put it back to this ion current into the main equation, then you have to solve it. But there are these constants, or the variables n and m and h. These are actually, again, something that gives you the understanding of relaxation time first, and then the relaxation level. So that in this sense, this is again that you put it again into it, and then you remember that those were and then M is was in fourth order, and then M is in cubic, and so on. You get very complicated equation, but physiologically correct. These empirical expressions, this relaxation time, tau, and this M and H, these, well, Hodgkin and Huxley found them it was ingenious understanding and mining the experimental data, and they got very special expression for that. When they did it, it was in the 50s. Just imagine about the numerical power of that time, in the 50s or in the 90s of last century. Some of the from our audience were not born yet, even this time, and this was a problem. This was a real problem how to get to solve numerically this equation, and there was a problem of convergence, there was a problem of accuracy, and there was a problem of the how to determine the velocity and all that. Now it's a different story, because now computer facilities are much stronger, and then we can really understand it. So there are three ion currents here in this one. And certainly it was possible to model first this threshold phenomenon. You start with a very small excitation, it will die out, nothing will happen. If you start above the threshold, then the pulse forms. Then the overshoot is described, and annihilation, so that if two pulses meet each other, the outcome is zero. They would, in the usual solid mechanics, the waves propagate through and then go on. Here, this is the basic is actually the diffusion type equation, and well, nothing comes out of it. What we did, we tried to just to put this in activity back. Again, it was a little bit tricky way, but we were encouraged also by some kind of experiments done by our Finnish colleagues who have measured the activity, also the brain and so on, although it is very small, but it exists. And the main point is just to get a little bit different model, and this different model, what we got here was something like the evolution equation type. It's a moving coordinate here, and this set is also the voltage, but scaled a little bit. That's why I used the different notation. And as you see that there are the nonlinearities here. This f is a nonlinear quadratic polynomial. Here it's usually the linear part. If we now try to find for such kind of evolution equation, which for those who are familiar with, say, KdV or Korteweg-Riese equation, or Berg's equation, or some different sign-cordon equation, this is something from that class. It describes one wave only. And the point is here that if we now try to understand the role of these nonlinearities, the main point here is that actually the roots of this nonlinear term were both positive. If we come to the famous van der Waals equation, both of the rules are one is positive and another is negative. So that actually it is somehow, well, similar to van der Waal, but not exactly. And our point was to understand whether this equation is able to explain the same sort of phenomena, like this sort of threshold, overshoot, and all that. It is one way, so we couldn't actually check this annihilation, but we tried to understand it in a little bit different way. Now what we did, and this comes again, for those who are familiar with nonlinear dynamics, quite an interesting story, because this is a nonlinear equation, ordinary differential equation, with the right-hand side, and right-hand side here is a sequence of delta pulses. If we now think about this hard problem and the sine node that sends every second a pulse, whatever the shape the pulse is, but something comes. Mathematically, it's very, very easy to use the delta pulses. That certainly it's not completely physiologically correct, but if we have the intensity and we have got the right period, then, well, this is a sort of, very similar to the problem. And now we try to solve it numerically. And nonlinear equation, once again, this f is nonlinear. So that there should be something, it might be interesting. And so it is. For example, if you start here and take this period fixed, period, this delta function is fixed, and you change this A or this intensity and go here. And now calculate what comes out of it. It's a sort of bifurcation diagram. Those who are familiar with Feigenbaum diagram would say that, well, it's something similar. The point is here in the middle with all that sort of thing. Is it chaotic or not? Now, the students should know what we have to calculate. We have to calculate the Lyapunov exponents. Lyapunov exponent, if this is negative, then you have got quite a well-behaved process. If this is positive, then it could be chaotic. The calculation shows here that this diagram here is this largest Lyapunov exponent over the same scale. As you see, 0 is here, and well, it goes like 0 for all this process. It seems that it proves that this is quasi-periodical. It's not chaotic. But would be another problem. For example, like here, we fix this A. Sorry, it's very sensitive. Fix A and change now the period B. So that's a different now. And then you see again there's some sort of bifurcations and all that sort of thing. And calculate once again the Lyapunov exponents. If you calculate the Lyapunov exponents, then you will see that the 0 is here. Well, there are regions. This is chaotic region, and this is chaotic region, quite clearly. So that this model actually gives a possibility to describe some kind of chaotic regimes. The next question is that we can calculate that. Many change the parameters and then try to understand and straight, as usually change the constants, and then you get a lot of these sort of time series, and then you have to really understand what is behind them. This is exactly now the same story like Feigenbaum did, that he collected all the results in one diagram. In one diagram with in the plane of A and B. And when we do that, instead of those trying to collect all those quite interesting profiles here, then we come to this sort of diagram, omega or period, as you see here, the horizontal, and in intensity of A was for the vertical. And now we have the very special regimes, all these over the threshold, under the threshold, period couplings, like here, also here, and some kind of transition region, which could also have some kind of CH, that means chaotic. Again, the problem is quite complicated in this sense that we can actually understand it, that very many regimes from one changing the parameters, excitation, the equation, the physiology, or is kept. But what happens with the excitation? For example, if we now fix some kind of intensity and start to moving, then this means that there must be a change. You come here, there must be a change, quite complicated change, for example, here again and again. This could be actually described in using the usual language of nonlinear dynamics, in this sense that we really understand that all these bifurcations, by not going into the details, what types are there, the Talnot or the Naimark type or whatever, but the most important is that we can also calculate the Lyapunov exponents for the same diagram. And then you see that it's starting from this yellow here and to red. This means that you have got the positive values. Means that in some cases, when you go from here, that nothing happens, it's all that regular. It's all positive, negative Lyapunov exponents. But when we go something like here, you change. You meet also the chaotic regimes. So this is something that is quite interesting, and we've had long discussions with cardiologists who, as you know, in medicine, they're very good to understanding all the cardiograms and all that sort of thing that are behind it, but we come from mathematics, and we had to find the common language just to understand each other. What quite interesting is that if I now go back here, then you see that there are a couple of these regions here which are, well, very complicated. Small change means that you have got something different. Indeed, if we work in these sort of regimes, then you would have a very nice and very, very clear sort of, the outcome. Then you have an external excitation, and then the regime is different. It could be also periodic or quasi-periodic, but it could be also chaotic. And to come out of it is again, you need an external stimulus. So that in this sense, it's really that after long discussions with cardiologists, they decided, yes, that it could explain something, but certainly we are not able to explain everything. At least this mathematical model is rich enough to explain something which is understood in physiology. So that it gives a sort of, courage to carry on some kind of analysis, that we published also a couple of papers along that line, and this is pretty well understood. But now, it's the next question. I still have time, I hope so. Is it only action potential? And now that's exactly what I said, that measurements show that there is also a mechanical way. And what kind of mechanical way? And what is the heat production? I'm not going to speak about the heat production, but I'm going to speak about the mechanical way. It's the experiment by Tasaki. So that they gauge. I'm really sorry that it's not so very well understood, but he tried to, I have to really to redraw. This is just taken from his paper. If we now come to this upper line, is actually the transverse the displacement. You can see a small white dot here, at least, and another one down here. Down here, so that actually you get something like that here, and the pulse is adjusted. There are other 10 years later. Again, so that the records the swelling, sometimes called, that it means actually that this nerve, the fiber, the wall, has got a tiny mechanical displacement, 2 nanometers, maybe around that, something like that. It might be that one needs a Japanese to measure it, because they are very good actually in doing such kind of very precise measurement. But this way or another, that it's measured. Even there is from this year, from the starting of this year, again, we can see that there are really something that is measured in the lobster nerve. So this phenomenon exists. And now the point is how to model it. I'm now going to speak about this modeling in this sense, that it's actually the nerve fiber, action potential going on, and what we are interested in is the intensity changes in this wall, which could be also taken as a sort of displacement. And again, some kind of schematic understanding when you deal with this lipid structure, what I showed also in the beginning, then this is really quite interesting. The usual situation is here and here, also that's a liquid phase, but this part where you have got this action potential, this is a little bit different. It is a gel phase, and the point is how to measure it and how to model it. Well, Heinrich Jackson have modeled this like shown here on this slide. Usual wave equation. Well, but the point is that the velocity, as you see here, c squared, it's that they say that this is related to the changes of the density. Non-linearly, u squared. Then they did the dispersion should be there. This was not very clearly explained. It was ad hoc term. They simply added the fourth derivative. And this is now the result is really quite interesting. Result is given here, and you actually understand this is the nonlinear equation. In terms of wave equation, really, you can see the acceleration, you can see the inertial force, and you can see this dispersion term. Dispersion term is, well, I put it in red because we are not very pleased with that. We say that you can't add just simply one term ad hoc. You have to understand the process, and from our understanding, it should be a little bit more. You can't just put just one term there and say that now it's done. And you can go to the dimensionless situation, and what they got the so-called soliton solution. They called it soliton. I wouldn't, because they haven't proved that soliton is really an entity that really interacts with others, and these are the changes which are related to the phase change, but the nerve pulse annihilates, so it can't be like that. And another point was that if you look at these horizontal measures here, minus 5 centimeters plus 5 centimeters, 10 centimeters, which is a little bit too much. What we did, actually, we also tried to calculate that the first thing is that what they said, it's a longitudinal. But we are actually measuring transversal. So that if we take now the rods, this is what we know pretty well from the solid mechanics, then we know that the transverse displacement is related to the gradient of the longitudinal displacement. So that this is the usual assumption, and that it's proved and it's understood pretty well. If we now go to that we have some kind of usual, some kind of this, let us call it soliton or whatsoever, solitary pulse, then, and you take the derivative of it, then it is really something that Tasaki has measured. So that this is again the same sort of understanding. And what we did, we added this term which is related, added in the blue. So it doesn't mean that it's well, something that we invented. This is simply related to the usual understanding from solid mechanics, that if you deal with a microstructured medium, you should take inertia into account. Otherwise, your velocities go to some kind to infinite. Whatever you might work in a good region, but nevertheless the limit goes somewhere that you do not like. And this model actually is really something that when we start with the sort of single pulse, then the derivative is pretty much similar to that was measured by Tasaki. So that again, the same picture, but I hope that you can still see this white dot up there, and also down. To know that this is something that is exactly like it is shown here. This upper dot, and this is something that's a lower one. So this is now the idea that we have also improved this model, and now we try to understand it. And that makes now the life very interesting. That actually this is, in terms of wave mechanics, this is called Boussinesq type equation. Boussinesq type equation was originally derived for fluids. So the name Boussinesq and what he did once upon a time, but also very much related to microstructured solids that Gerard Mojan from Paris, and we have been doing this, and some other groups. But it's different, because in solid mechanics you have this bottom type equation, as you see that. The nonlinearity is related to the gradient, ux. In this case, in biomembrane, the nonlinearity is related to U, displacement, and that's different. That makes the life, certainly from the viewpoint of mathematical physics, also interesting that if we leave now a little bit aside this biological phenomenon and try to solve this equation as a mathematician, then again we face very many possibilities and again the challenge is to come back after we have got all these sort of solutions, to come back and to understand what will happen. The interesting case here is that according to Heimburg-Jackson model, this coefficient P, the capital P there, is negative. And it means that actually if we now deal with the usual pulse, the nonlinear pulse, in solid mechanics, the front is actually something like that it should well, the discontinuity should happen at the front. Here it's vice versa, because it's a negative. The discontinuity actually starts to form here. So the pulse propagates to this direction here, and this goes sharper and sharper, which also is related to the formation of solid pulse. The question is now that, leaving aside now this bottom equation, which is actually pretty well understood also by Franco Pastrana, a couple of papers we wrote together, but this one is now pretty new. We try now to understand try to understand this influence of nonlinearity, so that the numerical data are taken from a certain range that we can't at the moment tell exactly that this is the experiment that we picked up in. Because this is really, we are trying to understand the internal life of this equation. And the method we are using for solving it is pseudospectral method. So that actually with these high order derivatives, they are included, that we can go to the Fourier space and then to solve an ordinary differential equation, and then return from the Fourier space back to the original space, and to get all these solutions. The accuracy is very good. We have been using it for a long time, and we know about the filtering, we know about the role of the frequencies, the high frequencies, and so on. So we are pretty sure that what the calculations are accurate. And now there are a series of such kind of calculations showing that if you start with a rather such a large pulse, then you come to the solid constraint. So this is one moment of that you see that it's starting to form. But again, Frank Pastrana knows it pretty well that if it should move to that direction, then these oscillations, or this should start here, not backwards. So this makes a thing completely different. And now, if we go now further on, we get a very nice train of the solitary waves. I can't. Well, actually, these are solid terms. We have found this ordinary differential equation. We have solved it, but we haven't checked yet exactly that whether this is something. Again, I repeat, it's a mechanical wave. It's not the nerve pulse. This is this swelling within the wall, and from those we have to go to the transfer. So that this is like a pretty complicated this procedure. But nevertheless, what we did, we tried to understand what happens with such kind of equations. And now there are certainly that which you change the coefficient as we usually do, you can get something that is similar to the Ericals, like this first one. You can get some kind of sequence of solitary waves. You can get also a little bit different, understand that what is the influence of the dispersive terms. You change this H1 and H1, for example, and it means that the velocity will be different because dispersion will certainly affect the velocity and all that. But again, this is not solving the problem yet, as you understand. The problem was that you have got the Merkels. It's action potential. It's electrical signal. Now, quite separately, we tried now to model what could happen in biomembrane. But we are not still able to put these two together. And as far as we know, nobody has done it yet. So that this is something that there are some kind of assumptions. We are very close to, we have some kind of working model, but I'm not able just to tell exactly the results. Maybe next year, it might be that maybe next year we are able to describe it. But this way or another, we understand the role of nonlinearity. We understand the role of these dispersive terms, which we think that it's better than just taking one term and adding it, because we really have we can use the Lagrange equation actually, but coming back to the academy. And certainly this is actually the main challenge now. How actually the structure of lipids influence this dispersive effect. There are several attempts to model it, also from the viewpoint of molecular dynamics, when you put all these sort of single molecules into account. It takes a lot of calculations. A couple of studies, we're now trying to put them together. And I think that the second one, to unite the models of action potential and mechanical wave, this is something what we are now very much interested in, and my co-authors, Kertam and Tanalbets, are now working very hard on that. And certainly thermodynamics. Heat, there are some estimations, some kind of measurements, but still not very well understood. What we did was many years ago already. We wrote a paper with Gerard Mosin on the thermodynamical viewpoint of this nerve pulse dynamics, so that just to understand how these classical models like Hodgkin-Huxley or Fitz-Nagumo and ours are described in thermodynamics. And the paper we just published in the beginning of this year, that's the biomechanical modeling and mechanobiology, this gives a beginning of that problem. But not all these figures I demonstrated with this formation of these solitons and all that. It's a very fascinating problem indeed, so that I do hope that we could continue, and if somebody in this audience and the younger people would like to join us, he or she will be very welcome indeed. So that we have been in touch with the Franco-Pastrana for so many years already, so that the ways and the links between the two laboratories, although, well, in the north and in the south, are pretty good. So, ladies and gentlemen, right now I've used probably all the time, so thank you very much for your attention.
Thank you for this dense lecture. As I said since the beginning, the subject is not easy, because the problems. There are so many. The objects to put in the model are so many, one must make some kind of distinction.
So you asked me to speak about that.
Yeah, sure. But what is important that, as always happens, but now you showed clearly that there are open problems which are quite interesting to study and to solve and to find the right mathematical or the best mathematical model we can find to describe this kind of phenomena which are quite important. I will just point out a small thing that I appreciate very much. We don't like to add ad hoc part in an equation. Just say, I like this, I put on and see how this will.
That's something
we must derive from some axiomatic, phenomenological, whatever you like, but we must, in some case, prove that it's necessary to avoid that.
Yes, absolutely, I agree. And that was exactly why we first, the first reaction that one cannot simply, be pleased with this ad hoc term only. We would like to understand why and what this means. And our this experience from solid mechanics, microstructure solids, and all that, say that we could actually prove that the two terms are needed. But as I said also here, the structure of lipids. This is something that it's again that the people also in our lab who work in actually they work on the diffusion through the cell membranes, so that we try to understand together with them that what is important. Well, they are interested in ion currents and the gates and all that, but nevertheless, the structure is something that should be understood.
Any question, comment?